The formation of zinc chloride. Mahat, do you know any acid-base equation that produces what acid should I use to make zinc chloride?
HCl.
Okay, so it's going to be HCl. And there are different ways of making. What do I react HCl with?
Maybe you can use zinc, zinc,
Okay,
zinc hydroxide.
okay, I can use zinc hydroxide as well, a base. Or I can use, I mean, there are three reactions. It's either a metal or a base, a metal hydroxide. This is also a base, a carbonate, right? So you had three reactions in which a salt would be produced. In the first one, hydrogen gas would be released. The same salt would be produced in these reactions as well. A water molecule is going to be produced over here, and over here, a water molecule plus carbon dioxide is going to be produced. Okay, Mahat, is this clear?
Yeah, it is.
I just and and you can use zinc as well because mazit metals they're used because they're not very reactive or very unreactive. So you can make your salt zinc chloride. In all three methods, the first reactant is insoluble. Zinc is a metal insoluble. Zinc hydroxide is also insoluble. Carbonate is also insoluble. But this salt, in all cases, the salt that's being produced is soluble. I mean, it's the same salt. So how do you make and how do you make a soluble salt from an insoluble reactant? Do you know the method of preparation?
Yes, I.
What is the method of preparation? I mean, what's the name of the preparation method? I mean, there were three methods. One was excess method. This was excess method. What you're going to do is you're going to take a beaker, right? And what you will do is you take this beaker and you start adding zinc to it. So put a piece of zinc in this beaker
And excess, right?
and in excess. You want it in excess so that all the HCl gets reacted, and
Yes.
the solution would have zinc chloride, and the gases would escape. I mean, if it's hydrogen gas, it's going to escape. Anyways, the excess zinc can be removed by filtration. So you can filter it out. Once this is gone as well, the solution would just contain zinc chloride and you would have to crystallize it. So going back to the question, where's the paper? One second. Where did the paper go? It's over here. Now going back to the question, so he's doing that. He's adding zinc oxide actually. Okay, so there's zinc oxide being added. So the reaction that he's doing is zinc oxide plus HCl, and that would produce zinc chloride plus H2 gas. Okay. Acha, name the apparatus used in step one to add the zinc oxide.
So where would the oxygen go?
Sorry, that's a water molecule would be produced. It's a base plus acid reaction. And it would produce salt plus water. So anyways, the first part is a small amount of zinc oxide. He's saying pour 40 cm of hydrochloric acid into a beaker, add a small amount of zinc oxide. Uh, how would you add the zinc oxide? What's the apparatus?
With the,
Remember, zinc oxide is a solid salt. I mean, do you know what apparatus? I mean, if you're cooking something and you add salt to it, you take a spoon. What's the spoon equivalent of? What's the equivalent of a spoon in chemistry lab? It's known as a spatula. Okay, so it's going to be a spatula. It's you're going to take a beaker. You're going to add it, fill it up with 40 cm cube of HCl, and you start adding the solid zinc. Mahad, is this clear?
Yes, sir.
Can you also check? Do you have the marking scheme with you?
For this paper, I don't. Yes, I do.
So ठीक है इसका देख लेना just a small amount of zinc and warm the mixture. So try and measure this. How do you warm the mixture? Bunsen burner. I'm just concerned whether they are asking us to measure the mass of zinc oxide or just to transfer the zinc oxide. Now next part is पिछला check कर लिए. Okay, next part is how did the student know that that the reaction had stopped? I can't hear you. Hello.
Yes, but when student doesn't come in, what
Like, I can't hear you, Mark. Can you type? Can you type? The next part is just 1 second. ठीक है. I mean, there is effervescence is wrong because there is no gas being produced, right? So there's no gas. So effervescence is wrong. No more zinc oxide dissolved. That's correct. Remember, you're only going to write the effervescence thing if there's a gas being produced. For example, in the other reactions, there was a gas being produced. I mean, if it were the first reaction, hydrogen gas is being produced. If it were the third reaction, carbon dioxide gas was being produced, but not the middle reaction. There's no gas being produced. So what is meant by the term excess? That simply means more than the required.
extra.
More than the required amount. Next is how is the excess zinc oxide removed? So you're going to. I said remember go through when you're doing ATP. Go through the any experimental type of question, electrolysis. These are all experiments. Salt preparation, that's important. Uh, Similarly, in metals, you anything that's related to experiments. Okay, that's going to be part of this. Rate of reaction, that's very important in this. So describe how the crystals are obtained. So you have to explain the process of crystallization, which is that you evaporate the solution to saturation point, evaporate the filtrate to saturation point, and cool gradually.
So can we say evaporate the solution to saturated form?
Filtrate and solution is the same thing. Solution is fine. I mean, I'm using filtrate because we've filtered it off. So what's left is the filtrate. But solution is fine. To saturation point and cool gradually. Uh, and then filter out the crystals that are formed. Suggest how the method would differ if zinc carbonate were used instead of zinc oxide. Uh, so how would the method be different? I don't think it's going to be different. It's going to be the same method. We need to check this whether I don't find any difference apart from the carbon dioxide gas thing. So the method would pretty much be exactly the same. Let me open because it's the latest paper, so one second. Let's have the marking scheme open as well, so our answers don't deviate. Okay, there was one. Okay, this is until saturated, etc. Evaporate. That's all fine. Everything is fine. This part, heating is not going to be required. For zinc oxide, he's using heating. But for this, heating would not be required. Carbonates react very well with acids. But I think the question was still kind of confusing because they were asking about the method. There was no heating required. No heating was needed. Next part of the question is: a student investigated the rate of reaction.
Sir, for part 1E, the difference would be that the carbon dioxide would be formed, right?
Yes, but another thing was that heating wasn't required. Like reacting bases, carbonates react very quickly with any carbonate. It reacts with acids. They don't need heating. As a singular part, a student investigated the rate of reaction between magnesium ribbon and solutions of dilute hydrochloric acid of different concentrations. So what's the reaction? It's Mg with HCl. What's going to be produced? MgCl2 plus H2. And he's using what is changing? Different concentrations. So you're having different concentrations. So different concentrations are being used. Now, a measuring cylinder was used to pour 30 cm3 of solution H. HIJK are all HCls, but different concentrations. So H into a beaker, 5 centimeter length of a ribbon was added. Timer was started. The time taken for all the magnesium ribbon to react and to disappear completely was measured. So the only thing is changing is the solution H. So different concentration. If the concentration is lesser, the reaction would be slower. So you have to first measure the time. This one I think is 0 minutes, and he's already labeled this. So it's 15 and 16 and 17 and 18 and 19, 20. I think it's 20. The ones are 16, 17, 18, 19. So it's 20 seconds. The next one over here is I think 34 seconds. Then this watch over here is 1 minute. The smaller arm is minute, and I think 8 seconds. And the last one is 1 minute and 38 seconds. So the concentration keeps decreasing. Now they were, as a one mistake that we made was if we were filling this table, the unit they were using was seconds. So we shouldn't be using minutes. This should be 68 seconds. And this should be 98 seconds. Like 1 minute is 60 seconds and 38 seconds, that's 98 seconds. Anyways, the reaction makes sense. The concentration keeps decreasing and the time taken keeps increasing. So slower reaction. As you go downwards, the reaction are getting slower and slower. So you're getting a lot slower reactions now. Anyways, experiment 5, solution J was added to magnesium ribbon. The gas produced was tested. The observations were recorded in the table. So, I mean, it's obviously hydrogen gas. The test for hydrogen gas is that it pops. Now you're being asked to plot the results. You can do that pretty much. I mean, we can try and it would be we can try and plot the results.
What is it for 5 again? For 5.
The experiment number 5. He was saying
Yes.
what is the gas that's being produced. So there was rapid effervescence, bubbles, and pop sound was produced when it lighted. That's hydrogen gas. We already know that it's hydrogen gas. I mean, magnesium with HCl.
Yeah. So what's the time for the
I said
consumption, right?
the experiment 5 is not about time. It's about testing the gas. So in experiment 5 is not he's not timing anything. So we basically just have 4 experiments. So I'm going to plot the graph. It's 2 minutes 20 seconds. So at sorry 2, if the concentration is 2, I'm going to plot total time कितना है 98 होना चाहिए. So I think one box should be 20 seconds. Sorry. I said when you're plotting graphs, one box should be 20 seconds because we have to go up till 98 seconds. This would be 40 seconds. This would be 60. And so on. This is 80. And this one is 100. Make sure the scale is big enough. It should cover most of the values and most of the graph paper as well. All of the values and most of the graph paper. So 20 seconds is a fine scale. It's so at 2 mole per dm cube the concentration was 20 seconds. Then if you go back, it was 34 seconds at 1.5. So at 1.5, it was somewhere over here, 34. I mean, this is 30. So this is going to be 34. And then if you go back, it's at 1, it's 68. So at 1, where's 1? 1 is over here, and it is 68. So I think this is 70. One small box is 2 seconds. And finally, the last one, it's 0.8 and 98. So at 0.6, 0.7, 0.8 is over here. So make sure you draw these pencil lines that, I mean, I'm doing this roughly. So 98 would be one box below 100. And then he's saying draw a smooth line graph. So use your free hand and draw this smooth line graph. It appeared to me a curve. Remember, when they talk about a line, it doesn't really mean a straight line. Okay? A line could be a curve as well. So you have to guess whether you're going to make a curve. Not all the points have to pass through them, but all the points should be close to it, and they should be evenly distributed above and below. So I'm going to see if it's a curve or it's, I said they haven't shown anything. I said show clearly on the grid how you worked out your answer. From your graph, reduce the time taken for at 2.5 mole per dm3. So I'm going to extrapolate this. Right, make it over here at 2.5. I'm going to measure the time. So we can go and have a look over here. You have to show the construction lines. Make sure with a pencil. So whatever it is, I think it's coming out to be 12 seconds. I mean, you can do it more accurately on a piece of graph paper. Why was the length of magnesium used? Why was the same length of magnesium used in experiments for a fair comparison? For a fair comparison, you want everything to be the same, except for the variable that you're investigating. Is that clear, Mahat?
Yes, sir.
I should then suggest the effect on the results of experiments 1 to 4 using repeating using 2.5 centimeter length of magnesium ribbon instead of 5 centimeter length. Or explain your answer. Using instead of 5 centimeter length of magnesium ribbon. Now, what would be the difference? If you're using a smaller length of magnesium, basically you're using lesser magnesium. So times would be lesser. Mg would dissolve faster because the piece is smaller. Like previously it was a 5 centimeter piece, so now the piece is much smaller, so it's going to dissolve way quicker. Here, suggest a different method which a student could use to investigate the rate of reaction between magnesium ribbon and hydrochloric acid. State the apparatus the student would use and the measurements the student would make. Now, I told you when you're measuring rate, you have to measure the speed with which something is changing. Now, in this comparison, I think what they are measuring is, what did they measure actually? They measured they measured how quickly magnesium dissolved. So what you could measure is you could measure the volume of hydrogen gas that's being produced. So you could measure the volume of H2 gas. The apparatus must be measuring syringe. Mahad, is this clear?
Yes.
Next one is use observations from experiment 5 to answer these questions. What type of chemical reaction occurs when magnesium ribbon reacts with dilute hydrochloric acid? So it's a neutralization reaction. The acid gets neutralized. Okay, let me. So the acid gets neutralized. Let me check that as well. अच्छा नहीं they talking about अच्छा ठीक है. They did not take neutralization. It was what they wanted was, this is incorrect. I said it was a displacement reaction or a redox reaction, because if you have magnesium reacting with HCl, then redox reaction is one where electrons are gained and lost. Mg is 0. Over here, Mg is 2 plus. So that means it lost how many electrons? Lost 2 electrons. And H is positive 1 over here, and H in the product is 0. So that means it gains electrons. So it's a redox reaction that's taking place. And identify the gas produced. It was hydrogen gas all along. So that's also done. Next question is about two substances, L and solid M. Solid L was ammonium sulfate. Now for this you need the salt. Ammonium sulfate is ammonium ions and sulfate ions. And we don't know what M is. Describe the appearance. It's going to be white. Only transition metals have colored compounds. The first portion.
So, what would be hydrated ammonium sulfate? Like, what do you mean by hydrated?
Hydrated means that there's going to be water of crystallization. Like the crystals will have some water in them, absorbed in them.
Okay.
Anhydrous salt is without water. Now, solid L was divided into two portions. The first portion of solid L was heated in a glass tube. A gas produced was tested with cobalt chloride paper. So, was heated. So, obviously, what is going to be produced? Water vapors, right? Now, water vapors is not the answer because they are asking for the observation. Now, cobalt chloride with water, in the presence of water, would change from blue to pink. Like if water vapors are added to cobalt chloride, if you have the data sheet with you, the colors of compounds. Do you have the data sheet with everything that needs to be remembered?
So the sheet.
Let me open this. I gave you a data sheet when we were doing acid, base, and salts.
Can you share it? Okay.
Just 1 second. Let me send this again 1 second. Let me open the drive. किस टाइम जा रहा था? अच्छा. Hello, Mahat.
Yes, sir.
So 1 second, let me quickly. This data sheet. Do you have this data sheet still? 1 second.
Can you share it again? I
It
probably
must.
have it, but it's I'm prepared.
So just 1 second. So I'm going to share it from my. It has all the tests. I'm going to share it now. Just look at the colors of compounds over here. Okay, so there are these colors of compounds. If you can see my pointer, hydrous cobalt chloride is pink. Hydrous means with water, and anhydrous is blue. So if they're adding water vapors and they're testing it with cobalt chloride, without water it's blue, and then it would change to pink. So cobalt chloride paper is being added. So that's what's going to happen. Remember, cobalt chloride is a test for water. Make sure you remember that and you remember the test. I'm going to send the sheet to you after this, okay?
Okay.
And the next one is the second portion of solid L was added to distilled water. The mixture was shaken to dissolve solid L. So it's being dissolved into two equal portions. An excess of aqueous NaOH was added to L. L is wait, wait a second. So wait a second. L is what is L? L is ammonium and sulfate. Ammonium ions and sulfate ions. That's L. Now the second portion. So he added NaOH. Now the test for the cations, NaOH. Look over here and find the test for ammonium ions. If you look carefully, where's ammonium ions? Where did the test go? Just 1 second. This over here. Look at the test. You have to remember all these tests. Ammonium ions, ammonia gas is produced on warming with NaOH. So that's what's going to happen. So this is all memorization. Nothing important to it. I'll send you the sheet. So if you add ammonium ions and you add NaOH to it, then NH3 gas would be released. And since it's an observation, it's a pungent smelling. And the gas was tested as well. The test for ammonia gas over here is given. It turns damp red litmus paper blue. So this test has to be performed. So the gas was tested to turns damp red litmus paper blue. The next part is dilute nitric acid and aqueous barium nitrate were added to the second portion of solution L. And you're being asked to give the observation. Now, this barium nitrate is a test for sulfate ions. You can have a look again and find sulfate ions. If you look over here, sulfate ions is you add barium nitrate and you get a white precipitate. So we have sulfate ions in our, initially it is ammonium sulfate. So you're going to get a white precipitate. So remember, this salt analysis part is all memorization. You have to remember all the tests. Mahad, is this clear?